Assalamualaikum. My name is Najaf and my roll number is 21TE06. Today I will be discussing lab number 2 of the subject digital signal processing, and the lab title is signal representation. The lab objective is of signal representation. In task number 1, we have been given the code and we have been asked to observe the effect of changing the value of n0. Secondly, the effect of changing the values of n1 and n2. And thirdly, dependency of value of x. In this code, the step signal x is generated based on the index n and a starting point n0, where the step signal is 1 for n greater than and equals to n0, and 0 otherwise. Now if we run this code, we see the respective signal. Now if we increase the value of n0 from -1 to 0 and then run the code, we see that the graph has shifted from -1 to 0, which means that our graph has shifted to right side. And if we decrease the value of n0 from -1 to -2 and then run the code, we see that the graph has shifted to left side. Thirdly, discussing the dependency of the value of x on n and n0, we can say that if n is such that n minus n0 is greater than and equals to 0, then the corresponding element in x will be 1. And if n is such that n minus n0 is less than 0, then the corresponding element in x will be 0. In task number 2, we have been given the code and we have been asked to observe the change by delaying the period and changing the starting and ending points. In this code, n0 is the starting point, n1 is the lower limit and n2 is the upper limit. And the line provided here will give you the desired step signal. Now if we plot it, we see the following graph. Now we will observe the effect of changing the delay period, which is the starting point n0. Here we increase the value of n0 from 1 to 3, and we see that increasing n0 will delay the onset of the step signal. Here we decrease the value of n0 from 1 to -2, and we observe that by decreasing n0 it will advance the onset of the step signal. Now if we talk about changing the limits n1 and n2, we see that by changing the value of n1 and n2, it will affect the range over which the step signal is plotted. We changed the range from -5 to 5 to -4 to 4, and we saw that the range was changed to -4 to 4. In task number 3, we have been given a script to simulate the exponential signal, and the second one is for the sinusoid sequence. And we have been asked to observe the changing effects of the values of alpha and n, and secondly changing effects of the values of amplitude, frequency and phase. So when we run this code, we get a graph for exponential decay, where the variable n is defined to represent the discrete index ranging from -3 to 3. The exponential signal x is generated using the formula 3 into 0.5 to raise to power n, where each value of n determines the exponent for the base 0.5. The stem function is used to plot the discrete point of the exponential signal. So if we increase the value of n, the value of 0.5 into raised to power n decreases, leading to exponential decay. the amplitude of the exponential signal is multiplied by 3, resulting in a scaled version of the decay signal. The signal starts at n is equals to minus 3 and decays towards n is equals to 3. Here we extended the range from minus 3 to 3 to minus 5 to 5 now, and it will show more samples of the exponential decay, allowing us to observe its behavior over a widened range of indices. Now we have changed the value of alpha from 0.5 to 0.8, and we saw that the amplitude has changed. By changing the value of alpha, we can control the rate of decay or growth of the exponential signal. Now if we run the second part of this code, we get a sinusoid sequence, and when we discuss about the effects of changing parameters, if we change the amplitude and if we increase the amplitude will scale up the entire causing signal vertically, and if we decrease it, the amplitude will scale it down. And if we change the amplitude, it will not affect the frequency or phase of the signal, it will only affect its magnitude. If we increase the frequency, the signal will be compressed horizontally, resulting in more oscillations within the given range of n. And if we decrease the frequency, the signal will be stretched out horizontally, resulting in fewer oscillations. And same like as in amplitude, if we change the frequency, it will not affect the amplitude or phase of the signal. Now if we change the phase of the signal, it will, adding a positive phase, it will shift the signal to the left, and if we add a negative phase, it will shift the signal to the right. And changing the phase does not affect the amplitude or frequency of the signal, it would only affect the horizontal position in time. In task number 4, we have been asked to write a function to simulate the unit impulse sequence. In this code, we have the range from minus 3 to 3, and we have made a function with the name impulse sequence. Now if we run this code, we get the respective unit impulse sequence for the range of minus 3 to 3. In task number 5, we have been asked to write a function to simulate unit step sequence. Here the range for the step sequence is from minus 4 to 4, and the function we have made is of the name step sequence. Now if we run the code, we get the respective unit step sequence graph for the range of minus 4 to 4. And as unit step is 0 for less than 0, we don't get any value for the values less than 0. In task number 6, we have been given two functions, and we have been asked to solve and perform these functions using the functions used in task number 4 and task number 5. So the first function was about impulse sequence. Here n is the length of the sequence. The step sequence was the function that we made in task number 5, and impulse sequence is the function that we made in task number 4. So if we plot this, we get the following graph. Here for the sequence of the function x of n, we have a unit impulse function which is subtracted from 3 times of unit impulse function. Now for the second function, n is the length of the sequence, which is 7. The values are from minus 3 to 3, and if we plot this graph, we have a sequence of x of n in which it is 3 times into unit step of right shift by 3 units plus unit impulse into 2 times right shift plus n times negative shift of unit impulse function. In task number 7, we have been asked to write a program that is able to flip the given signal. Here we have taken the original signal as 1, 2, 3, 4, 5 and we have made the function flip signal in which the original signal will be flipped. Then we used the function display and then we plotted the graph. If we run this, we see that the original signal was from 1, 2, 3, 4, 5 and the magnitude was minus, for 1 it was 1, for 2 it was 2, for 3 it was 3 and so on. But if we see the flip signal, here the magnitude at 1 is 5, for 2 it's 4, 3 it's 3 and so on, and we see an exponential decay signal, whereas the original signal was an exponential growth signal. In task number 8, we have been asked to write a program that is able to perform index scaling on the given signal. In this code, we have given the original signal as 1, 2, 3, 4, 5 and we have defined the scaling factor, that is 2. We made a function with the name scaled signal in which we scale the original signal by the scaling vector and then we plot the signal. So if we run the code, we see that the amplitude at 1 is 1, whereas if we see the amplitude scale signal at 1, the amplitude is 2, so the signal is scaled by the factor of 2. In task number 9, we have been asked to write a program that is able to shift the given signal. Here in the code, the range for the unit step signal is from -5 to 5 and the factor by which we are time shifting the signal is 2. In task number 10, we have been asked to write a program to simulate zero order hold. So in this code, n underscore original, which is the function, we have given it the range from 0 to 9. The original signal is from 1, -2, 3, 0, 4, 2, -1, 3, 2, -2. And the sampling parameters, we have sampling frequency fs is equals to 2. N underscore sample is the function and it tells the time indices for the sample signal. For zero order hold operation, we made a function with the name sampled signal and we have used for loop to perform the zero order hold operation. So if we run the code, we get a graph like this, where the original discrete signal was given in samples and in zero order hold sample signal connects the samples and it holds the value until the next sample is reached. In the last task, which is task number 11, we have been asked to write a program to simulate first order hold, and the hint given is y is equals to mx plus c, which is the equation for line. So in this code, we have given time instants, the signal values. We have also defined the hold time and we have made a function with the name sample signal, and the code below the sample signal functions demonstrate the first order hold operation, which is also known as linear interpolation. If we run this code, we get a graph like this. Here the original signal was in discrete samples, whereas in the first order hold sampled signal graph, we see that the discrete time intervals that we have taken are of an analog signal. So after taking the samples, we hold the values of that sample constant until the next sample is taken. And for interpolation, when we take the next sample, we interpolate between the current sample and the next signal to estimate the signal value between the two sample points. So first order hold is simply a conversion technique used in signal processing, which is used to convert analog to digital.